So this is the very first lecture on linear algebra. So we start this lecture with providing a physical example. Then we explain what is meant by point vector. Next, we formulate some sort of equation and then express that in a matrix format. And finally, we also describe what is meant by linear combination. So first, let's draw something like that. So we have this, for example, this. So we have something like that. That is a 2D space, two-dimensional space basically. And here it's a board. Here we have this line of action. And a similar line of action here. It's a rough sketch, so it's not really precise. But let's say these two guys here, this one and this one, these are two line of action. We have a ball here that can move along this two dimension. Now along each of this line of action we can create force in both direction, in this direction or this direction, and here as well we can create force in along this direction or the other direction. So if this is say F1, this is F2, we can create a outward force going in that direction or inward force like this direction. So for example, the outward force can be created by using a plunger mechanism, or the inside force can be created using a vacuum system. So these are our actuator system. Now the task is like we want to control the motion of this ball. So this one we want to move, and we want to control where we want to position this. So along this whole two-dimensional board, it can be moved anywhere. That is our purpose. Now the question is, can we actually do that? So, and how can we actually do that? So the design procedure of that we will explain. So this is our physical system. All right. So this one is done, and yeah, so we want to control the location or the position of this ball. Now the next question is, what is actually impacting or what is actually controlling this ball? The ball is getting controlled by the forces F1 and F2, but the forces let me get my pointer. Okay, the ball is getting controlled by these two forces, but what is actually happening, like the input, if we consider this ball is being impacted by this particular actuator, so the input is a force and the output is a displacement. So the corresponding displacement for F1 is say say I define it as alpha. Alpha is a displacement, and this is a vector. So let's just write this way. This is a vector. F1 is also a vector. Similarly, for F2 is also a vector. When F1 acts on this, there is another force that acts on this one, which is beta. So beta and alpha are displacement vector. And typically we relate F1, so our displacement, say alpha, is somehow is proportional to the force F1. So according to Newton's law, it's F is equal to ma, and A can be somehow connected to alpha. And we can find out some physical law to fit into it, but I'm not going to the deep quantification of the force and displacement. Rather, I'm more interested in how alpha and beta can be adjusted to find a way to control the position of the ball, or to end up in a position where we actually want the ball to be at. So that means we need a good control on alpha and a good control on beta. So this will eventually mean that we need to control force F1 and force F2. All right. So that said, we need to understand what is alpha and what is beta. So as I said, these are vector, and we call them point vector. How or why? So let's do this. Let's draw this this coordinate system where we have this one as alpha 1, alpha 2, beta 1, beta 2. This is a point, this is a point. So what does it mean? It means that when F1, we apply F1 on this ball, this will move. Like, we consider everything else is stationary, and only F1 is working on this. And this ball will have a final position. So this final position is presented by, is provided by alpha 1, alpha 2. Similarly, if only F2 works on the system and nothing else works, or F1 is 0 or everything is stationary, then the displacement of this ball because of this force is beta, and the final position is beta 1, beta 2. So these are the final point for each of this force, or representing the displacement. So now these points are important, and from where we measure this is important. So typically we measure this from the origin. Say our origin is this 0, 0, as we are considering a two-dimensional system. Alright, so this is our final position, and say this is P1 and this is P2, and so the vector alpha 1 is gonna be OP1, and the vector, not alpha 1, this alpha, sorry, and the vector beta is gonna be OP2. And here OP1, OP2, or alpha or beta, these are our point vectors. All right. Now, say we want this ball to reach to a certain position, like somewhere here, for example, or say somewhere somewhere here, for example. which we define as B. So B is B1, B2. So this is the final position after both the force acts on this ball. Then we can find out another vector, another point vector, which is this. So let's define it as P3, and then this one is the resultant vector, which is OP3 equal vector B. And then we can write an equation that this vector and this vector, if we sum up, we get this final vector. So alpha plus beta equal B. So this is our equation. Now the question is, so this is like exactly showing the magnitude of alpha and the magnitude of beta is perfect, and we are getting to this point P3. But it might happen in real case. We want to achieve any point in this 2D plane. So if I draw this, so along this whole 2D plane, we might want to achieve any single point here, which might be this point P or might not be this point P. So in that case, we need to adjust our force F1 and F2 in a way that we can achieve those points. For example, a point can be right here that we want to achieve. So in that case, the forces needs to be adjusted. So we need to say, if this is F1 and F2, we need to probably add a weighting factor W1 and W2 to make this W1 F1 plus W2 F2 to achieve this point. And the value of W1 and W2 is something that we need to determine. And this actually changes. This changes depending on the position of this this point, the final point. So that means if the position of the final point, this point, the position of this final point changes from this one to this one, we need to adjust the force, and at the same time the displacements will also be changed. So there will be a weight associated with this one that is going to be changed. So let's consider the weights that changes for the weightage that change for the displacements are x and y. X and y. In that case, these are basically multiplication factors, and this might eventually help us to get to a desired point that we want. I can give an example by just simply copying this, and then let's use this. So I'm simplifying this whole thing. Alright, so this is alpha, and we have this beta. we have this beta here. Now say we want this point something, say here we want to achieve something here. This is our final point P3 and this is our B vector. So can we achieve that? So definitely if we sum this up, what happens? So with the current version of alpha 1 and alpha and beta, what we get is, if we sum up, we have alpha going from this point to this point. Now from here we basically start beta. So we're talking about this equation. We're talking about this equation here. So first we go from 0 to alpha, this distance, and then we have to add beta. So beta is gonna be parallel to this one. So I'm just drawing a parallelogram. And then I kind of get this one. This one is replacing beta. And so this is gonna be the final position of B. So if we just add alpha plus beta, this is gonna be B. So that's what we showed in the previous image or picture. But we cannot do that because right now our B is in a our final vector B is in a very different location. So this is here. So how can we achieve this? So we can see that we can do that by, so alpha, we can take a negative multiplication factor to turn this vector. Right now this vector is going this direction. So if we can somehow take it to this direction, and then from here if we can make a parallel line along this beta, then we can get this final point. So that's why this same equation that we had before, we can turn it into a more generalized equation, which is alpha x plus beta y is equal to b. So this is just a generalized equation where x equal 1, y equal 1. So, and then alpha plus beta is equal to b. This is a specific case, but this one is a more generalized case, which works for everything. Now, for example, here, x is probably, alpha is probably going this direction, alpha is probably going to this direction, but when we are considering alpha x, it's probably going this direction. So alpha x here is gonna be, say, something like this. So this is gonna be alpha x. And beta is this direction, but we can make this thing beta y. So then alpha x plus beta y turns out to be b. So here this magnitude is not necessarily this magnitude. This is gonna be we can measure this and this one and divide. So the relation between this thing and this thing is so if this the beta y over beta, so if this this is the old beta naught, and this is the new beta 1, then y is gonna be this quantity, which can be anything, and this is our weightage for vector for vector y, for vector beta. All right, so this is our basic equation. This is our this one is our basic equation that we have for 2 dimension, and from this we can start writing in terms of our coordinates. Right now, if we see the this image, we have this alpha can be determined in 2 dimension by alpha 1 and alpha 2. So we can write this way: alpha 1, alpha 2, and we have the weightage, plus we can write beta 1, beta 2, y equal b1, b2. So this equation is the most important one. Let me just make a copy of this. So all right. So right now we have this this final equation here. That is the equation that we have formulated, and we know what is x and y. X and y are basically weights to which these columns should be combined to get the final variable. And this form is also called linear combination of vector alpha and beta and the resultant is b. So this is what we call linear combination. And if we really see, we can change if x, y are our weights. So if x and y both are, so if we can write x, y element of real number, and there is no constraint, that means x can be minus infinite to infinite and y can be minus infinite to infinite, right? In that case, we can indefinitely change the values, the magnitude of the displacement vectors alpha and beta, and get any point, and can get any point on this board. Therefore, our scope, or the extent to which we can reach, or we can position the ball using our 2 actuator, is any point in the in this board, and therefore if the final point for the final point, if this is like, if y is a say, not y, if say we determine uh, another variable z, which is gonna be r square. So basically in 2 dimension it can reach any point. This is going to be output position of the ball. Alright, so that said, if I remove the whole thing, we can also express this in matrix form. The matrix form for this is going to be alpha 1, alpha 2, beta 1, beta 2, x, y, b1, b2. This is our coefficient matrix A, this is our decision matrix X, and this is our output matrix B. So this is our matrix form. And we can always get this in the by multiplying the simple matrix using the simple matrix multiplication, alpha 1x plus beta 1y equal b1, alpha 2x plus beta 2y equal to b2, and this turns out to be the same equation, but this one we can always write in this way. So the coefficient of x goes together alpha 1, alpha 2 plus x, and coefficient of y goes together beta 1, beta 2, y equal b1, b2. b1 and b2. Now here another interesting thing is this one was possible. So for this system we could achieve any point on this board in 2 dimension. This was because these two vector alpha and beta, these guys were the two vectors alpha and beta, these guys were linearly independent. That's why we could get it. We could get this we could get any point on 2 dimension. Now to give an example of this, let's make a copy of this thing and take it to another page. Let's take it to the next page. All right. So see, we could reach to any random point by using our vector alpha and beta. The reason for this is like these vectors are not dependent to each other. They're different, and that's why they could reach any single point. We can just multiply this by any number or any weight and multiply this by any other weight change direction, whatever we do, and then we add this together to finally get this. But there is a case where it might happen that this might look like this. So this might look like this, where alpha is this, and say we have beta we have beta that looks like this. And now say we have a point. We have a point that is P a point P, and we have the same equation, alpha x plus beta y. And with this combination, can we ever get to this point? Or say if we have a vector, this vector is b, can we ever get the vector b by with this combination? The answer to this is no, we cannot, because no matter how much whatever scaling factor we multiply our vector alpha with and the vector beta with, the summation of that can never reach to that point. But yes, we can reach to, if p were only on this point, only on this straight line, if p were only on this straight line, then we could achieve that, but right now we cannot. So we can see that when alpha and beta are along the same line, then we cannot achieve two-dimensional achieve a vector that is a two-dimensional location and not on the same line. So in that case, we can also see that there is a relation between alpha and beta. So we can write that beta equal, say, another weightage factor multiplied by alpha. So we can multiply alpha by some weighting factor. So for example, here it looks like it's 2 times alpha, and we can get beta. So beta is nothing but actually a scaled alpha. So even though it looks like we have in two-dimensional system we have two vector, in reality we actually have one actual vector, and another vector is not providing us real information. So this is a matrix. In that case, we have the matrix alpha 1, alpha 2, beta 1, beta 2. This is gonna be just something like this, say alpha 1, alpha 2, alpha 1, alpha 2. So in that case, we say that this is linearly dependent, and also we can say that this matrix A is singular, it is singular, and also non-invertible, and also we do not have unique solution for this. So it's important that for a two-dimensional system, if here when we design this thing, this should have a certain angle in between them. a certain angle in between them. If these are in the same direction, then alpha and beta, these are going to be basically same vector but scaled with a different multiplication factor, and this is gonna limit to what our ball or our object can be moved. It can only be moved along this direction, because when f1 and f2 are in the same direction, then the displacement can only be along this direction. But if there is a slight angle difference between f1 and f2 by an angle theta, then we can create two different vectors, and by scaling these two vectors and summing them up, we can achieve any single point on this space. So this same concept applies for 3-dimension, 4-dimension, and n-dimensional space where it's difficult to understand. So for example, the same thing could be defined as the same point could be defined as a 3-dimensional thing. So let's just take a copy of this. So right now this is two-dimensional, but it could also be considered as 3-dimensional thing. So in that case, it would have been alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, and b1, b2, b3. Right? Even though it's a two-dimensional thing, we can consider the same thing as 3-dimension. So on the same physical system, this is a 2-dimensional thing, but we can also add a third dimension. Only the third component, alpha 3 equal to beta 3 is equal to b3, all is going to be 0. But if it's not 0, if it's a 3-dimensional thing, then we can describe that the same way. Similarly, this could be considered as an n-dimensional point, an n-dimensional vector. But other than two component along x and y direction, every component along every other component is going to be basically 0. So the same vector we can, if we write alpha 1, alpha 2, beta 1, beta 2, right? X, Y, Z, X, Y, Z, 0, 0, B1, B2, B3 is going to be 0. And this is also going to be 0. So it's a 3 by 3 matrix. So we can write this way. Which turns out to be alpha 1x, beta 1y plus 0 into z is equal to b1, alpha 2x plus beta 2y plus 0 into z equal to beta b2, 0 into x plus 0 into y plus 0 into z equal to 0. So all three valid equations, but actually there are two useful equations. So if there were any component in the z direction, we can also make this structure useful. Similarly, the same thing can be written in n-dimensional. In terms of n-dimensional space, the only difference is going to be everything else is going to be 0 other than x and y axis or coordinate system.